So now let's see how this is done in practice. So the problem statement that we are going to look at is the one from the blog, right? From Vitalik's blog, and it's a simple equation, which is x3. What is it actually? You see, x3 plus x plus 5, and this is the calculation that we want to do, and the parameter is so the public parameter is 35. So you want to say that you know an x for which x cubed plus x plus 5 equal 35. Right. So the first part of the step to form this proof is to prove that we are actually evaluating this particular function. We're doing this calculation, and then that the result that we're getting is 35, and we know this x for which this matches. So so what we're going to do is first step is to switch from this. Well, there's only one here, but normally there will be several steps, several assignments, and several formulas like this. For hash, it would be way more complicated than that. There's like hundreds of steps. So we want to break it down to steps that are smaller and that have a very specific form. And the form that we have is you want to only use statements that are of the form you can introduce intermediate variables, and you're only allowed to multiply and add the previous values. So in this case, we can introduce y, which is x cubed, and then we do y plus x plus 5. And that's exactly the same thing because we use substitute, and you have the same value. And furthermore, if you this is still too complicated because x cubed is not a multiplication of two terms. It's like x times x times x. So we're not allowed to do that. What we must do, let me see if I still have it on, is do something like y. I should use actually letters because I'm gonna start to run out of these letters. So let's use a. So a equal x times x. Right, so multiplication, you can do multiplication and addition of two previous values. So x is your secret and it's one of the values that you have. So that's okay. Then you can continue with b, where you do a times x. So that's okay because it's a was a variable that was introduced earlier, and you're allowed to multiply a previous value with one of the values that you have. So the values that you always have in the beginning is 1 and x. So you can always use 1 and x, and then anything that you introduced earlier. So that's why I can do a equal x times x, and then you can do b equal a times x. So this is also the same. So obviously this is x2 and this is x cubed. Then I want to do x cubed plus x plus 5, but here I can't do the double summation, so I have to break it down 2 steps. So I do b plus x, and And then finally I have D, which is C plus 5. So when I reach D, D is equal to, so this is equal to x cubed plus x, and this is x cubed plus x plus 5. So this is our stuff here. So far so good. And another way to draw this is with wires and boxes. So here what I do is that every time I have a new variable, so I have 1x a b c d. I say that these are wires that go into a box that represents this operation. So for example, if I have x times x, I have my wire x, right? And then that guy goes into a box, so x and x, and then that box calculates the product of x times x, and then the output will be a, right? And then a is combined with x again, and that gives me b. So that's another multiplication that gives me b. Then I have x again. Okay, this drawing is going to be very, it goes into another box, which is a plus box, and then the output is c, that goes into a plus box with 5. So you have a series of boxes which are called gates, and because these are like the transistor gates or the logical gates are in hardware, and each of these wire, so we have the wire X here, the wire A, we have the wire 1. Each one of these wires, they carry one of the outputs. You have 1, 2, 3, 4, 5, 6 variables. So we have 6 variables, and we have 4 equations. So 4 equations for 4 gates and 4 gates. Right? So this is something it's going to help us figure out the dimensions of the stuff. So this conversion going from this problem statement. Oh, so we have another condition, of course, is that the output here, D, should be equal to 35. So we do this proves that you have done the if you follow this circuit, you have done this particular calculation, and then the constraint at the end is where you say that your input, your x, is the solution that you're looking for. Yes, it's 35. So this transformation here is the transformation from the problem statement into an arithmetic circuit. So circuit because you have like wires and gates, and it's arithmetic because these are arithmetic operations, multiplication and addition. So that's the first step. So this is called your arithmetic circuit. Circuit. Yeah, arithmetic circuit. So now we have this. We go to the next step where we turn this into a set of constraints. And to do so, what we do here is we look at we take these variables and we'll put them into a list. So in the terminology of this stuff is called a vector, but it's basically a list of n values. So here we have 6 variables, so we have a list of 6 values, and our solution S is going to be a combination. It's going to be the assignment of the these values. So we start with 1, right? We have X, then we have A, we have B, we have C, and we have D. Right? So for a given X, you can calculate through this, going through these wires, and then you would have a value for A, value for B, value for C, value for D. So for example, if you do X equals 3, so you would have 1, 3, then A is 9, 3 times 3, so we know that. And then B is 9 times 3, 27. And then C is 27 plus 3, so it's 30. And then D is C plus 5, so it's 35. Right? So with you have one possible assignment for this S by choosing the starting point of for S, sorry, and by choosing the starting point of X. So this is one vector. But if you choose X equal 2, then you're gonna have a different S. Obviously, the last one, D, would not be equal to 35, and this would not be a proper solution because you also have the constraint, which is D equals 35 somewhere. Otherwise, it's not a solution. So now that you have this, but we want to express these relations in terms of in terms of multiplication by a vector. So if you have one vector like this, we want to say that this is this should have the form. So we're looking for a vector A, which has also the same dimension, B and C, so 3 vectors, also the same dimension. So it's going to have 6 values here, 6 values here, such as A times B, sorry, A times X. So this is times multiplied by B times X, so it's minus C equals 0. So this is the relation that you want to keep. And so this is the relation you want to keep, right? So it's always gonna be this relation. So it's not the only time we're gonna see this one. And this is because we want the special form for this equation, so that it's called a Rank-1 Constraint System. So they have this form, and this product here is a scalar product. So the scalar product is calculated if you have 2 vectors. So for example, this one and this one, they have to have the same dimension. So this one is okay because it's actually 6 and 6. And you do this product by multiplying term by term. So this one we multiply by this one, this one, this one, and then you sum the result. So the X here is your X, is your solution, right? So it's called S, but I should call it S here. This is really S, right? So let's say that the first one, we want to have the first relation be X times X. So what I do is I recognize that there's already a product here, right? So we have the product here, right? And I want to have A and B only pick up the term X, because it's X and X. So to do that, I put a 1 in front of the X. Let's do this term, right? This 1. And then I don't need any of the other guys. So I will put 0, 0, 0, 0, 0, and 0. So we have 6, 0. 1, 2, 3, 4, 5, 6. And then the B terms, I also need to pick the only the X in the vector S. So I want to put 1 here. And again 0, 0, 0, 0, 0. and then C would be 0 0 0 0 0 0 0. Right. No, I'm sorry, and C would be A, right? Because we want to have this basically equals C, right? We remove this term here, it's equal to C. So let's verify, because we want A here. So I want to pick the term 1 in front of the C. So put 0 0 0 0 and 0. Right? So let's verify. If I do the product of A times S, scalar product of A times S, I would be multiplying 0 as 1, 1 plus X. So this is going to be 0, this is going to be X, and everything else would be 0. So I'm not going to pick anything that is A, B, C, D, because it's all multiplied by 0 here. The only thing I'm going to pick with this multiplication is the term X. So this is actually, in this particular, it's going to be equal to 3, right? If I do this, it's going to be 0 0 0 0 0 0. So all these guys are 0, right? And then 1 times 3. So I have 3, which is the X term. And then B is the same, because B is actually the same vector. So if I do multiply by B scalar S, I also pick up only the terms in X. So this is actually X times X, right? And then equal, so this is a statement that I want to do, C, so I multiply this vector C by this vector here, right? Which is also right, so this is so the C terms here would do the product of this vector 0 0 1 0 0 0 with this guy. So 0 times 1 is 0, 0 times X equals 0, 1 times A equals A, and all the other guys are going to be 0 as well. So this is going to be X times X, and then the C scalar S will give you A. Right, so do you have this first relation? So with this first combination of 3 vectors, there's 3 vectors here, and that particular statement here, a scalar S multiplied by B scalar S equal C scalar S, you have expressed this first equation. So equation 1. This is equation 1. Right. So then we continue with equation 2. So let's do equation 2. Equation 2, page, and equation 2 would okay, let me keep that, guys, so that I have a reminder. We have equation 2, which is A times X. So again, well, I write down my make sure it's still on the easy to see. I still have my 1x A, B, C, D, which is my my vector S, right? And now I want to express B equal A times X. Right. So again, I lift A from this this vector by putting A equal 1 0 0, no, so 0 0 0 1, sorry, super stupid, 0 0 1 0 0 0, right? So this multiply to this guy, and then the only terms that are remaining is this 1 times A, which is A. Then the names are pretty bad, because this little A is the name of the wire of this terminal, and this guy, this A here, is a different A. It's the A of the equation here, A times B times S. So I hope it's not too confusing. So the second one, this X here, would be I want to keep the only factor, which will be X. So same as before, I'm going to do 1 0 1 0 0 0 0. Right, and then finally this should be equal to b. So c is gonna be taking this value b only out of the wire. So it's gonna be 0 here, 0, 0, 1, 0, 0. Right, so this second set of ABC is going to be our second equation. Second equation. And then we can do the third one. So this is the second set. We do the third one, which is C equal B plus X. Right. So you notice here that this is no longer multiplication, and so therefore it's going to be a bit different, because we were dealing with multiplication only before, but this stuff here. But you also notice that this obviously is equal to b plus x multiplied by 1. So our a would be this guy, and our b would be this guy, and c would be the outcome. So what you do is now the a have to do this combination b plus x, which it can, because we can do any linear combination of these guys, right? So if we want b plus x, we have a vector that we don't need the 1, so we put 0 here. We need the x, so we put a 1, so that this 1 times x equals x. We don't need the a, so it's going to be 0. We're going to be the b, so it's going to be 1, and then 0, 0. Right? Remember that we do scalar product between this guy and this guy, this guy and this guy. So the scalar product is by multiplying term by term, and by doing the sum of all the values. So this 0 times 1 will be 0. 1 times x will be x, and then this term here. And then 0 times a is 0, 1 times b is b, so we have this term, and then 0 and 0. And then the other side, the b side now, well, we only need the 1, right? And we have the constant 1. That's kind of why we need to have one part of this vector. So that's going to be used by saying that this time we only want to pick this one here, and nothing else, none of the real variables. Right, and then C again is going to be the output C, right? So it's going to be only 1 on the last term, on the 1 to last term, 0, 0, 0, 0, 1, 0. Well, that was a little bit different, but pretty simple as well. And finally, this is the third set. And then we have the final equation, which is D equal C plus 5. Right. So same thing happens here. We want to pick up C. Since it's a plus, we're going to also do the same thing, where we say C plus 5 multiplied by 1. Right. So C plus 5, we do A is equal, we need the 5. So 5 is, we put a 5 here because it's going to be 5 multiplied by 1 here, right? When you do the scalar product. So 5, by putting 5 here, we have this term 5. And then we don't need x, so it's going to be 0. We don't need a, we don't need b. We need 1c, so it's going to be 1 here, and d is 0. And then b is the same as before. We have 1, 0, 0, 0, 0, 0. And finally we have C, which is we're going to take the last term D, so 0, 0, 0, 0, 0, and 1. And this is our final set of it. So we have 4, right? 1, 2, 3, 4 sets of constraints of this form. Right, so I'll put here again, a scalar x times, so this is a vector, this is a vector. When you do a scalar product of two vectors, you have a value. You just have one value of scalar, because every term is multiplied and do the sum, so it's going to be one single value, no longer a vector. So it's called a scalar, and this is a scalar. So you can multiply a scalar by another scalar, so a value by a value, and this is should be equal to c times x. We have four sets, so 4 sets of this form, and in each set we have 3 vectors. We have a vector for A, a vector B, a vector for C, and the vector has size 6 because we have 6 variables. So this transformation going from this arithmetic circuit, right, into is the one that is going to the R1CS, Rank-1 Constraint System. So constraints is because we have this particular equality constraint, and it's a system because we have several of them. Right. So that's a very one. It's pretty systematic, and again, it seems like we do this stuff without a real purpose. It's more like it seems like it's pointless. But the goal is is to reach a point where we have turned a problem that we don't have a solution for. We like finding the Zk-SNARK for this guy is not an obvious problem, to another problem which is equivalent, for which we have a solution. So even though the two problems will look like very unrelated, the fact that there is a transformation that goes from one to the other means that if we have a solution or a mechanism to work out a proof for the second problem, then we have also a practical solution for generating a proof for the first problem. So we have now reached the point where we have this R1CS. Right, we have this R1CS, which is basically A1, right, to A6, B1 to B6, and C1 to C6. Right, and then there's the other constraint that D equals 35. But actually, I will start omitting it, because you can say that this constraint here can be injected inside the same stuff here by saying that there's one more constraint which is gonna lift the wire D, and then is gonna say that D equals 35. Right, so this looks really similar to this one. Right? So for simplicity, I'm gonna ignore this one later. So this is the R1CS. But this is not the end, right? So the next step really is it's turning this set of constraints, which we have like four sets of constraints, right? Because we have 4 gates. We want to turn that into one set, but instead of using just scalars, these guys are going to be polynomials. So the same set, the same form here, but instead of operating on the value, so just x equal to this guy is a particular value, right? This is our vector. We're going to use the polynomials.